Athan レーネさんです。A さんはですね、stdlib っていう、JavaScript のライブラリーを作ってメンテナンスも活動している方ですね。で、stdlib っていうのは、その名の通り、JavaScript の中での標準ライブラリー、標準っていうのはJavaScript T サテが切ってる標準じゃなくて、よくこういうの使うでしょみたいなユーティリティが集めたようなやつですね。で、それを結構去年、実は A さん去年も来てくれていて、去年来た時は、その stdlib の話と、その中で WebAssembly を使って高速化するみたいな話をしてくれたんですよね。で、今回はちょっと趣向を変えて、リアルタイムマシンラーニングっていう話をしていただくところです。じゃあ、よろしくお願いします。じゃあ、拍手お願いします。
Great. Thanks for coming to this talk on real-time machine learning and JavaScript. So, my name is Athan Reines. I work full-time on an open source project called StandardLib, which is a standard library for JavaScript and node.js with an emphasis on numerical and scientific computing, including machine learning. So, the talk overview is as follows. First, I will introduce machine learning and define some foundational concepts. Next, I will motivate why you should care about machine learning, and in particular, real-time machine learning. Next, I will discuss machine learning as it applies to JavaScript. I will then walk through a few examples showcasing real-time machine learning in JavaScript. After which, I will offer some tips and tricks about applying machine learning algorithms. And finally, I'll offer some conclusions and additional resources you can use to get started using JavaScript for real-time machine learning. If I move too quickly, this talk is online, so you can revisit during and after the conference. Simply go to my GitHub page or follow me on Twitter, where I'll tweet out a link after the conference with the talk slides. So, machine learning. Machine learning is applied mathematics and statistics and largely resides in the domain of computer science. In contrast to the field of statistics, where we focus on mathematical formulas, the derivation of robust estimators, and developing mathematical techniques for modeling problem domains, in computer science, we focus less on mathematical purity and more on the practical aspects of writing algorithms which can run efficiently and with high performance and give us results which are good enough. The primary aim of machine learning is to find patterns in data, to find the proverbial signal in the noise via numerical computation. To describe those patterns that we want to find, we formulate and we train models. A model is a mathematical formulation summarizing the nature of and describing the relationship between data variables. Models serve as the statistical foundation for machine learning. In order for machine learning algorithms to find patterns in data, we must train or teach these algorithms as to what those patterns are. And in a sense, machine learning algorithms learn the models to describe particular patterns, and that learning often comes in the form of learning specific values of coefficients within an equation. For example, in this equation, here the coefficients would be a sub n minus 1, all the way to a0, whereas the particular values would be xn minus 1, etc. As a more concrete example, suppose we want to predict the temperature tomorrow. A naive approach would be to predict that the temperature tomorrow is whatever the temperature is today. And our naive approach can be expressed mathematically using this equation, T sub n equals T sub n minus 1, which is to say that for a given day n, the temperature should be equal to the temperature of the previous day. This equation is our naive model. However, we might perhaps rightly believe that this naive approach might not be as accurate due to, say, day-to-day temperature variability, i.e. noise. For example, an anomalous weather pattern may lead to extreme variation, going from a very hot day to a very cold day right in a row. But for most climates or regions, such extreme variability would not be normal. So one possible refinement would be to predict that the temperature tomorrow is the average of the temperature of the past, say, 7 days, which will be represented by this equation. So by taking the average, we will smooth out some of the day-to-day variability and hopefully have a more reliable estimate over the long term. In other words, by using the average temperature of the previous 7 days to predict tomorrow's temperature, our predictions will be closer. We'll have a smaller error on average to the actual temperature than had we used our initial naive model. And we can generalize our model by using the parameter W in the third equation, which simply represents the number of days we want to average over. It could be 7, it could be 3, it could be 30. It doesn't really matter. This is our generalized model. So in this example, the model is the mathematical formula describing the computation of the average temperature. And that model is trained by giving the model data. For example, the temperature over each of the past 7 days. And in this case, the output of the trained model is simply a single value. And that single value is the average, is used to predict the next day's temperature. How we train learning algorithms comes in 3 varieties. The first is batch. Batch training means training a model over the entire data set. In order to accommodate new data, we must retrain our model by performing batch training over the entire updated data set again. Each time we get new data, we have to retrain it. Many big data MapReduce style algorithms, such as those run on Hadoop, are of this variety. The second is incremental. Incremental training means training the model incrementally, one datum at a time. Such an approach allows us to continuously update a model as data arrives, without having to retrain over the entire data set. The third is mini-batch, which is a hybrid of batch and incremental. In this variety, we buffer data and we train models in small batches. The primary motivation for mini-batch is the ability to achieve some of the robustness of batch training within a reasonably close approximation and achieve some of the immediacy of incremental training, meaning we can achieve near real-time computation. And this brings us to real-time machine learning. For the purposes of this talk, I define real-time machine learning as the subset of machine learning algorithms which support incremental training. That means as a new datum arrives, I can update my model incrementally. Meaning in order to generate a new prediction, I don't need to store and analyze all past prior events. I can simply update an existing model. Now, just as a matter of clarification, commonly due to perhaps marketing departments, you'll see machine learning approaches and technologies often labeled as real-time. These approaches are probably more accurately described as near real-time, in which due to distributed computing strategies and or parallelization, they allow for retraining and analysis to be done more quickly than traditional batch analysis. My definition excludes these near real-time approaches. Why this limited definition? Because I find incremental machine learning algorithms particularly compelling, especially when used in JavaScript environments such as web browsers and node.js. Now, why are incremental algorithms exciting? Incremental machine learning algorithms allow for model training and prediction/classification to happen concurrently. I don't need to decouple these 2 aspects of training and prediction, meaning in practice, for particular types of problems, I don't need dedicated infrastructure or processes/threads for training and separate infrastructure, such as client machines, for prediction. Often, incremental algorithms have low memory footprints, making them suitable for IoT and other resource-constrained devices. Why is this important? For the following reasons. First is privacy. Incremental machine learning algorithms allow data to stay on device. For example, the Apple Watch has an API to get raw heartbeat data. So with incremental machine learning, I can train a model, for example, learn a user's normal heartbeat pattern, and then detect when a heartbeat or set of heartbeats no longer fits this pattern. In this scenario, I never have to send this data to a remote server in order to do the analysis. I can do it on device. And because I don't have to send data to remote servers, analysis has low latency, it works offline, and can be more power efficient. And finally, as analysis can occur on device or using newer buzzword technology at the edge, we have direct access to all device sensor data, which removes the need for often complex data serialization and deserialization logic. Now, to help motivate real-time machine learning use cases, let us consider some real-world data streams. So in JavaScript environments, such as the web browser, we have data streams such as mouse and cursor movements, scrolling, and clicks. In the web browser, on mobile devices, and in Node.js, we have access to sensor data, such as device orientation, temperature, and ambient lighting, all data which is collected continuously. And finally, we also have monitoring data as an example of a data stream, such as logs of failed HTTP requests or server errors, etc. So what can machine learning, real-time machine learning, allow you to do? We have already discussed one use case, and that's forecasting or prediction. So the naive model we formulated earlier, which involved computing an average in order to forecast tomorrow's temperature, can be formulated as an incremental machine learning algorithm. Each day we record the temperature, use that temperature to update our model, and make a forecast for the next day based on our updated model. For the UI interaction data that we discussed in the previous slide, such as cursor movement and scrolling, we can generate a prediction as to what resource a user will most likely need next, allowing us to create what would feel like a faster and more efficient UI. In fact, one example I've actually seen in the real world is where the application will literally track cursor movement across the web application, and based on the velocity and orientation, they will predict what UI elements can be clicked, and before a user actually clicks on that element, a fraction of a second before, they'll go ahead and make the HTTP request, such you get an immediacy of the resource refreshing your web page. Right? That's an example of a machine learning use case within a real-time web application. Another classic use case is anomaly detection, such as detecting a malfunctioning system or fraudulent activity. In this classification task, we want to detect when a datum or set of data is different from the rest, because the sooner you are able to classify new data as anomalous, the sooner you can fix a potential problem. A third use case is clustering, which is the process of assigning groups. As an example, we could collect device performance metrics such as CPU utilization or memory usage, and identify different application states, such as resource intensive or idle, etc. And based on the number of states and how frequently they are occupied, this could be informative for on-device resource planning and optimization. So at this point, hopefully I've convinced you just a little bit why real-time machine learning sounds useful. But why do any of this in JavaScript? Especially when there are other languages that you could do this in, such as R and Python. So as a practitioner who has written and used machine learning algorithms in other languages, I can confidently say that JavaScript is as equally qualified as those other languages such as R and Python for machine learning tasks. However, the stigma that JavaScript is not suitable for math, and by association machine learning, persists. So I'd like to take a couple moments to dispel a couple myths. The first myth is that JavaScript has poor performance. So as part of our work on standard lib, we've run the benchmarks, you can run them yourselves, they're publicly available. JavaScript environments are just as fast as, and more often not faster than Python and R. Modern JavaScript environments are highly optimized and they're continuously improving. With WebAssembly and Node.js native add-ons, you can readily achieve near native performance. The second myth is that JavaScript is somehow incompatible with mathematical computation. The argument in support of this myth typically goes something like single-threaded, something, floating point, something, 64-bit integers. And what is clear about the people making this sort of argument is that they have not used other languages for scientific computing and machine learning, because these arguments in favor of this myth can be equally applied to these other languages, such as being single-threaded or non-native 64-bit integer support, or floating point operations. People can, and most importantly do, write robust and performant mathematical code in JavaScript. I can point to standard lib and the thousands of mathematical functions that we have implemented in JavaScript for doing mathematical computation and machine learning. This said, some languages do offer syntactical features, some advantages such as operator overloading, which allow for terser syntax. But these things are not limiting and certainly don't prevent you from actually writing mathematical computation in JavaScript. The primary reason why people do not currently do mathematical computation and machine learning in JavaScript is that other ecosystems already have a critical mass of libraries and frameworks for doing mathematical computation. The issue is not one of technical limitations. The issue is one of community support, which is something that I and others are currently working to address. So, to help dispel the previously mentioned myths, I want to turn now to some examples demonstrating machine learning in JavaScript, and not just any machine learning, but real-time machine learning. So the first example is going to be anomaly detection, and to help structure this example, I created an observable notebook. Let's zoom in here. Okay, get a little bit bigger. All right. So I mentioned that this is going to be real time. For the purposes of this talk, the sensor data is static, meaning I've already previously loaded the notebook and it's a finite size. However, all the analytical components which follow are all amenable to real-time analysis. They are implemented as if the data comes in real time and continuously updates a model. So in order to get started with our analysis, what we do is we load some libraries. This is standard lib, project that I work on along with others. This is the sensor data set. We then have various incremental accumulators. These are the incremental machine learning algorithms. In particular, these are simply for computing various statistical properties of the data set, such as the mean and standard deviation. And then we also define an incremental accumulator for performing Grubbs test for outliers of data assumed to come from a normal distribution. The basic idea of Grubbs test is a statistical formulation that was developed in the 1950s that tries to develop a test to figure out if the maximum or minimum value within a univariate data set, meaning of a single variable, is an outlier or not. And it tries to do it with some kind of robust probability. And then finally, I'll define some other aliases. One is for a KS test, which allows you to determine if data does come from a normal distribution. And then there's some other utilities such as the plot API. So kind of the first step, whenever you're working with any kind of data set that you want to try to apply a machine learning algorithm to, that you want to take is exploratory data analysis. We want to actually look at what this data set actually is. So we load the data set, and then we can examine its contents. What we see is that it's an array of about 20,000 items, and each item in that array consists of an object with various properties. Such as the reading number, the mote ID, where mote here refers to the sensor in the network, a flag, whether the sensor is indoor or outdoor, and humidity and temperature readings. I then define a function, which this is a nice utility function. It's not that important, but basically allows me to pluck out various sensor data for a particular sensor ID, which we can then use to pull out that data, such as the readings and the temperature. And once we do that, we can take a look at the plot of that data set. And what we see from the plot is that we have some kind of baseline behavior around 27 degrees Celsius, and then around reading 2200, what we see is a huge spike. This could be an anomaly, an anomalous event. So just to look at some other data sets, we'll look at the another mote ID, this is a sensor ID within the network. And what we see is that we have a similar baseline behavior, but yet no spike in that data set, which suggests that maybe in the previous data set we did actually see an anomaly. And the goal of this notebook is to try to figure out, can we develop a real-time machine learning algorithm which would identify that particular anomaly? So remember that I said that the particular test that we're going to use for real-time anomaly detection is Grubb's test, which assumes normality, meaning that the data comes from a normal distribution. It looks like it's bell-shaped. So we need to first verify that. And how we verify that is using a statistical test called the KS test. So we run that test, and what we end up finding over the entire data set, we end up finding that the data is not normally distributed. And in fact, if we had gone back and if we had updated this, we would see that the data is not actually stationary. So even though there's small noise fluctuations, the statistical properties of it vary over time. So we wouldn't actually expect that this data is normally distributed. And in fact, that's what we can statistically confirm in an automated fashion using the KS test. However, what we might think is, even if globally the data set is not normally distributed, what if on a very small time scale, if we divide up that data set into small little chunks, into time windows, we could test if the data is normally distributed within those time windows. And if it is, then we can start applying our statistical tests within those time windows to identify anomalies. So in order to help us with that, what we first do is we find a smoothing function, which is going to take a moving mean, or running average, over that data set to help smooth that out. And if we look at that, we notice that the data, while it still has some non-stationarity, meaning its statistical properties fluctuate over time, we do reduce the noise. And what reducing the noise allows us to do is it helps eliminate some of those small variabilities while still retaining the large variabilities which we're interested in, which are those large-scale anomalies. So once we've done that, we are now ready to do a sliding test for normality. And so we have this function which does a normality test along the data set. And in order to figure out what the optimum window size is, what we're going to do is we're going to define a series of windows over which we want to conduct this test. And we want to choose that window size in which we get the fewest failures in normality. We want to find the optimal window size that our data remains normally distributed. So when we do that, and we plot that data, what we see is that around a window size of 20 data points, so roughly about a minute and a half of data, we have a minimum in the number of windows which are not normally distributed, which is great. So if we use this window size and we go across, we can start applying Grubb's test to identify anomalies within the data set. And so we can apply this with an outlier detection algorithm in which we define an accumulator. This is our model, our machine learning algorithm model, in which we're going to update incrementally with each new data that arrives. And what we find is that when we run this control and we plot it, we don't actually identify any anomalies, which is great. But that's our control data set. We didn't expect to find any anomalies in that data set. How about if we apply that to our test data set? So we do the same thing. What we do is we do another KS test. We can easily confirm that the data is not normally distributed. However, we can also do it where we do the local, the running test. This is just a smooth data set. And what we find by doing the windowed KS test, meaning looking for regions of normality within the data set, is that we end up finding more windows within our first sensor data that are not normally distributed. And so that gives us kind of like a hint that maybe we can identify outliers in this data set. So what happens when we run that same outlier detection algorithm on this data set is that we do, in fact, identify that anomaly. And the nice thing about this, for this notebook, is that we've done all this in JavaScript, and all client side. We didn't have to communicate with the server to run anything on some distributed backend, whatever. You can do this all within your browser and in your applications to look for anomalies. So the second example that I want to look at is real-time k-means clustering. So clustering is another task that we can use for real-time machine learning. And I'm going to hope that this loads. There we go. So once again, we load the library. We define some random number generators for doing simulation. I have to say that in this data set, what we're doing this time is we're using simulated data. And the reason why you want to use simulated data is because it allows you to control how data is generated and also understand where the source data actually comes from. And then we have here's our machine learning implementation, which is our incremental k-means. So this is our real-time machine learning algorithm. We have some simulation code. It's not really important. It's a discrete time hidden Markov chain. This means that from each state to state, we have state transitions in which we define our path through a particular network. And what this data looks like when you actually plot it is it looks something like this. And what we can see is that we have two larger globs and maybe some hidden structure within those globs. And having the advantage of simulation, we can actually label that data according to the underlying state. And what that looks like is it looks like something like this, where we have 5 different clusters of data with some overlap between those clusters. And the goal of our real-time machine learning algorithm is to be able to identify and extract out the centroid positions of those clusters. So what we can do is we can initialize that our cluster implementation. We then simulate some cluster data, or simulate some our data. And for each datum that we simulate, we then update our incremental machine learning algorithm, and then we record where that machine learning algorithm believes the centroids are. And when we actually plot this, what we find is something like this, is that where you see kind of these faded out spots, this is the machine learning algorithm learning where those individual centroids are over time, in which they finally settle on with these dark orange circles where the centroids are located. It's a rough approximation, but fairly accurate, right? And we did this all in real time, once again, incrementally. So there are other examples which I don't really have time for, such as regression and classification. If you're interested in these things, just check out the standard lib repository, where you can find online stochastic gradient descent and online binary classification examples, etc. So, some tips and tricks. So the following tips are generally applicable regardless of whether a machine learning algorithm is written and used in JavaScript. And the first tip is to use simulation to generate synthetic data sets to run against real-time machine learning algorithms so you can better understand an algorithm's capabilities and limitations. Next, always, always, always perform exploratory data analysis. This means exploring your data by plotting and performing basic analyses in order to get a feel for your data, in order to test basic assumptions, as we did in those notebooks when testing that the network sensor data is normally distributed. Because if those assumptions are violated, you could end up applying the wrong machine learning algorithm. Next, while true in general, but particularly for real-time machine learning algorithms, what makes these algorithms performant is two things. The first is data structures. One such data structure is n-dimensional arrays, or ND arrays, which are single-segment, contiguous blocks of memory. And these data structures allow for more efficient task optimization. Another common data structure is a circular buffer. And while the textbook definition is simple, these need to be implemented carefully in order to avoid poor memory management, especially when implementing them in JavaScript. Next, certain real-time machine learning algorithms require specialized tree data structures. An algorithm would be like for quantile approximation. And the second key thing for writing performant real-time machine learning algorithms is choosing the right algorithm. And one example of where this is really critical is quantile approximation. A naive approach would be to buffer all the data, sort it, and redo this every time you get a new data point. A better approach would be use an approximate method based on trees with a certain tunable error rate. And batch analysis, especially for one-off analyses, we can be okay using a naive algorithm or less efficient data structures. However, in the context of real-time statistical analysis and machine learning within web and node.js applications, this is not viable. So there are 3 points that I want you to remember from this talk. The first is that JavaScript is perfectly suitable for mathematical computation and machine learning. And not only is machine learning in JavaScript possible, but doing so introduces new types of applications which offer better data privacy, better performance, and better resource utilization. And in the words of Brendan Ike, always bet on JavaScript. The second thing I want you to take away is that real-time machine learning algorithms require using the right data structures, regardless of what language they're implemented in. And third is that real-time machine learning algorithms require using the right algorithm. So with that said, I'd like to thank you for coming to this talk. If you have any questions, you can come see me later. And if you're interested in knowing more, if you want to find out some more machine learning examples, etc., check out StandardLib. There's the repository. Then follow me on Twitter, etc., and I'll tweet out the link. So thank you very much.
結構あれでしたね、アノマリディテクションとか、パッと初見で聞いた人が分かりますか、異常値検知とか、多分結構アルゴリズム難しい話多かったかもしれないですけど、GitHub 上に彼の、スライダーもすでに上がっていて、そこを読むと結構分かりやすいんじゃないかなと思うので、ここ見てみてもらっていいかもしれないです。なんかアルゴリズムの話とデータ構造の話と、あとは JavaScript がいかにマシンラーニングで向いてるかって話とあり